Hello and welcome. Today we're going to be going over optimization and absolute extrema formative that we've done in the past classes, but in particular I'm going to be going over how to find the domain in these optimizing and absolute extrema questions. And I know that these can be very tricky, but it's going to lead to correct answers and more points if you figure out how to do it correctly. So, in the first problem, a rectangular field is bounded by a fence on 3 sides and a straight stream on the 4th side. Find the dimensions of the field with maximum area that can be enclosed with 1,000 feet of fence. First, we want to draw a diagram. So, we have a rectangular field, that's the actual fence, so something like this. And then we have a blue stream going like this. So, really we're just trying to, and then we label the two sides, so we can call this side x, this side would also be x then, and this side would be y. So this is our diagram. We won't count this side because it's covered by a stream. We don't want any fencing there. Okay, to find the optimizing equation, we want to in the question, we are asked to find the field with maximum area. So we want to optimize the area equation to find the correct answer. So we can call the area equation A, just for simplicity, and make that equal to x times y. The constraining equation is something that's always true, and we are given that we need to use 1,000 feet of fence, no more, no less. If you look at the diagram, to use this 1,000 feet of fence, we need to add up this x, this y, and this x. So our constraining equation would be 1,000 is equal to 2x. Oh, hold on. 2x plus y. These are our two equations, and now we need to find the domain. To find the domain, you need to look at the constraining equation. A simple trick to remember this is because you're trying to find domain constraints, and so to find domain constraints, you check the constraining equation. Next, you set both variables equal to 0. So in this case, we set x is equal to 0 and y is equal to 0. If x is equal to 0 and we plug that into our constraining equation, we get that 1,000 is equal to y. So y is equal to 1,000. And then 1,000. And then if y is 0, then we get 2x is equal to 1,000. So x is equal to 500. What we do by setting both variables is equal to 0, if we want to find in terms of x, which you should do basically every single problem because x is the main variable, so we're trying to find it in terms of x. We're trying to make the constraining equation in terms of x as well. So you would make the domain in terms of x. When you set x is equal to 0, you're basically checking if if a solution can exist, theoretically, just that if y can exist. So in places where y is approaching infinity, so y is going to infinity or going to negative infinity, then you can see that x equals 0 is not included in the domain because y is going towards unbounded numbers. But in this case, y is equal to 1,000. So y is kind of defined basically and can be defined. So we include our 0 in the domain, so 0. Notice that we set x is equal to 0 because x cannot be negative. You can't have a negative fence value in feet. You can't have negative 5 feet of a fence. And then when you set y is equal to 0, you're checking the upper bound of the domain, which is what is the x. So in this case, x is 500, so our domain let's here. So our domain would be 0, 500. And we'll be going over another place of how to find the domain later. But right now, our domain is 0, 500. So now we need to put the optimizing equation in terms of x. So using this constraining equation, we have y is equal to 1,000 minus 2x. And putting that into our optimizing equation, we have a is equal to x times 1,000 minus 2x. And a is equal to 1,000x minus 2x squared. Now we need to write that initial statement that we're going to be using the extreme value theorem. This is very important because if we don't write that initial statement, then you're definitely going to get marked points off of, because you're not using like the standard format, and you're not like informing whoever's grading your test that you're using extreme value theorem. So in this example, you would say, since A is continuous on the domain 0 to 500, the extreme value theorem guarantees an absolute maximum. So guarantees an absolute maximum. Why does the extreme value theorem guarantee an absolute maximum, and why are we writing this instead of guaranteeing absolute extrema? Is because absolute extrema also includes the absolute minimum. However, in this case, we're asked to find the maximum area. So we want to find the absolute maximum of the area equation. So you would write, since A is continuous on the domain, the extreme value theorem guarantees an absolute maximum, which is what you're trying to find. Let's erase this, but this is how you should structure your initial sentence, how you're going to say that you're using extreme value theorem. Since we have our area function now in terms of a single variable, so we can take the derivative of this. So a prime of x is equal to 1,000 minus 4x. To find critical values, you would set a prime of x is equal to 0, and you would find that x is equal to 250. Now this is the only critical value, because the a prime can't be undefined, and this is the only value where it's 0. So we do a candidates test, and make sure to do the candidates test on the actual area function. We include endpoints, so 0 include critical value 250, and 500, which is the other endpoint, and we find a of x. 0 and 500 would give zeros, and 250, you can if x is 250, right, you would put that back into the constraining equation. So you'd get 1,000 is equal to 500 plus y, so y is equal to 500, and then you would just multiply these two, which would be 125,000. So you would write your answer in terms of the context of this equation. So you would say the dimensions that maximize. Okay, so that's maximize the area of the field is 250 feet by 500 feet. And that should be your answer. Make sure to always write your final answer sentence in terms of the context of the situation, otherwise you won't get full points. And if you follow these steps, you should, for every single optimizing question, you should get full points every single time. Now, the second problem, a company who sells foam filler in 8-yard cube increments wants to minimize their packaging costs. Find the dimensions of a square base box with the smallest surface area that will hold 8 yards cubed of foam filler. So our diagram, I'm a little bad at drawing these kind of box thingies. That. You connect this. Wow, that was really bad. Okay, but your diagram. Shoot. Okay. Your diagram should look something like this. Hold on. Let me try and make it better. So. This. This is a little bit too far. Okay, yeah, there we go. So this is what our diagram looks like. Notice how it says a square base box. So the base, let's just call it the base side length x, and the height would be y. So now we need to find our two equations. So our constraining equation is what always has to be true. So we need our volume to be 8 yards cubed. So 8 is equal to x squared times y. X squared. X squared times y. And our optimizing equation, what we want to maximize or minimize, in this case we want to minimize surface area. So our surface area equation would be, let's call it SA for surface area, 2x squared plus 4xy. Now we need to find our domain. So our domain is, So our domain, you would set both variables is equal to 0, x is equal to 0, and y is equal to 0. But notice how in this case, if you set x is equal to 0 on the constraining equation, you're getting y is equal to 0 as well. So, and that's just 8 is equal to 0, right? 8 is equal to 0, which just plainly does not work. So there's, like, x equal to 0 does not work. And doesn't work. And y equal to 0 is the same thing. It doesn't work. However, if you can see, if y is actually approaching 0, so I'm just doing the arrow for approaching. If y is approaching 0, then that means that x squared is approaching infinity. If you think about it, 8 in the equation 8 equals x squared times y. If y is some really small number, let's say like this, then x squared would have to be really big for it to equal to 8. So x squared is going to infinity when y is approaching 0. And if you think about x squared approaching to infinity, it's also that x is just approaching to infinity. I think you could square root both sides, but that doesn't really make, you don't need to do that. So it's just x is approaching infinity. So our domain, since x is equal to 0, plainly doesn't work. But if y approaching to 0 makes the x approach infinity, that means that our domain is 0, infinity. Mr. Froome said, or whoever your teacher is, they said on the worksheet with the answers that to not get too hung up on this, it's not that important, but it might be important in the future, and it's better if you get a good grasp on it right now, because you're going to need to define the domain. However, the domain would be given, I'm pretty sure, in optimizing problems, so that's that, but it's just good if you can find out the domain. So x x approaching infinity would be our upper bound, and then x is equal to 0 would be our lower bound, but we don't include 0. So let's just delete this. Now we need to show our work and justification. So our surface area, we want to write in terms of x. So surface area, so let me just erase this. And surface area, the constraining equation in terms of x would be y is equal to 8 over x squared. So putting that into our surface area equation, we have 2x squared plus 4x times 8 over x squared. This, and this is just 2x squared plus 32 over x. And then if we want to find, so we don't immediately say that to the initial sentence that you're going to apply extreme value theorem, because you can't, there is a discontinuity at x is equal to 0, because that would make this entire equation undefined. So you don't say that. Also, no, never mind. It's not a discontinuity at x equals 0, because we're not even defined at x equals 0. We're not including x equals 0 in our domain. Instead, if you take the limit approaching to infinity, x approaching infinity, of the surface area equation, 2x squared plus 32 over x, what's the highest power or highest exponent? It's 2x squared. So limit x approaching to infinity of 2x squared. And this is just does not exist going to positive infinity. Since it's going to positive infinity, an absolute maximum does not exist. So you would write, so there is no absolute maximum. And you would see the same results for the limit of x approaching to negative infinity, because you're squaring the x. So you would write this, and it actually works out in our favor because we want to find the absolute minimum anyways, but you need to write there's no absolute maximum. And if you write any sort of limit work or end behavior, then you don't need to write like the initial equation, the initial sentence saying that extreme value theorem guarantees an absolute minimum, maximum, or absolute extrema. So we can just erase this, but make sure to always check the end behavior and use limit work on discontinuities. So we take the, derivative of this equation, and you would get 4x minus 32 over x squared, I think. And then you would set this equal to 0, 4x minus 32 over x squared. We would multiply both sides by x squared. So times x squared would be 0. Let's go up here. 0 is equal to 4x cubed minus 32. 4x cubed is equal to 32. X is equal to 2, I believe. Yeah, x is equal to 2. And you would also see that x equals to 0 is also another critical value, because that would make the derivative undefined. It would make the derivative undefined, but we're not including x equals 0 because it's not in our domain. So with the critical value of x equals 2, you actually realize that since we need to, let's just erase this work. So we know that the critical value is x equals 2. Erase this. Now, if we make a standard candidates test, right, you would not include the endpoints of 0 and infinity. You would not include the endpoints of 0 and infinity, because you can't take the values of that. Instead, what you want to do is you want to just do a simple y-sign test, because we have only one relative extrema, which is at x equals 2. If this is our only relative extrema and we're not using any, and we know that there can't be an absolute maximum, we're not including endpoints, this must be an absolute extrema as well. So to prove that it's a relative minimum, which we want to find the absolute maximum, you would just do a y-sign test of 2. And you would see that it's negative here and positive here. So x equals 2 is a relative minimum. Now, I'm not gonna, I'm gonna abbreviate the final sentences, but it's just since surface area is continuous, so I'm abbreviating continuous with one relative extrema. The relative extrema is absolute extrema. So the let's go up here. So the relative minimum at x equals 2 is an absolute minimum. Therefore, we want to connect our final equation back into the context of the problem. So you would say a base length, base length of 2 yards minimizes production cost. You won't say it minimizes surface area because that's not in the actual context of the problem. The context of the problem is, we wrote over it, but it's basically the packaging cost here. So you want to say that the base length of 2 yards minimizes the packaging or production cost for the company because that's the actual context of the situation. And that is how you find the domain of these kind of questions. It's a bit confusing, but it's really helpful. And that's also how you solve these kind of optimizing equations, how you include your limit and end work when it needs to, and how you write your sentences if you want to use extreme value theorem, or your final sentence with the context, or like if there's only one relative extrema, it's an absolute extrema. So thank you, and see you later.